Hello. We continue our discussion on electrode potential, but this time we have a non-standard condition. In our previous discussion, the electrode potential that we obtain are at standard condition. That means the solutions, the ionic concentration is at 1 molar concentration and the temperature of the Voltaic cell or your galvanic cell is at 25 degrees Celsius, and for gases they are maintained at 1 atmosphere. Okay, at the standard condition, the equation that described a cell potential in this condition is called the Nerst equation. Okay, and the formula is the potential at a non-standard condition is the potential at the standard condition minus this factor. You have RT over NF, the natural logarithm of Q. Where Q is in chemical equilibrium, this is the product of the concentration of the product divided by the product of the concentration of the reactant, each concentration raised to the power of its stoichiometric coefficient. So for the hypothetical reaction where you have A moles of A and B moles of B will give you C moles of C and D moles of D. The Q is written as the product C raised to its coefficient, stoichiometric coefficient, product D raised to the stoichiometric coefficient, divided by the product of the concentration of reactant A raised to its stoichiometric coefficient and the concentration of reactant B raised to its stoichiometric coefficient. You have learned this during your previous discussion on chemical equilibrium. Okay, the F is the Faraday constant with a value of 96,500 joule per mole of electron. Okay, and N is the number of electron that is transferred in the redox reaction in the unit of mole electron per mole of the reaction. And R is your ideal gas law constant with a value of 8.314 joule per mole Kelvin. If you take the base 10, this is the natural number, ln is the natural number, we can take it using the base 10 logarithmic, wherein we have the factor of 2.303, the log of Q. Again, Q is your KEQ, as in your lesson in chemical equilibrium, okay, which is also called the reaction ratio. Okay, so at room temperature of 25 degrees Celsius, which is 298 Kelvin, we can simplify this factor since R is a constant, F is a constant, and if the temperature is at room temperature of 25 degrees Celsius or 298 Kelvin, we can have these three as constant. Okay. So this 3 and that factor will be equal to 0.0591 volt. So if we plug in this factor here, we can have 0.0591 volt over N, the log of Q, or the log of KEQ. Again, this equation is used only if the condition is at room temperature of 25 degrees Celsius or 298 Kelvin. Let us have an example to illustrate the use of the Nerst equation. Okay, we have here 1/2 cell in a Voltaic cell is constructed from a copper wire dipped in a 4.8 times 10 to the negative 3 molar solution of cupric nitrate. The other half cell consists of a zinc electrode in a 0.40 molar solution of zinc nitrate. Calculate the cell potential. Okay, we have here a schematic diagram. Okay, from the previous discussion, we am referring to your activity series. Zinc is above copper, so zinc would be at the anode and copper would be at the cathode. Okay. So we're given here the concentration of the copper solution of the cupric nitrate is 4.8 times 10 to the negative 3 molar cupric nitrate. Okay. On the other hand, the zinc nitrate is 0.4 molar zinc nitrate. Since nitrate is very soluble in water as an aqueous solution, they are highly ionized in water. Okay, so in this compartment, in your anode compartment, you have the zinc ion present and the nitrate ion as well. Okay, in your cathode compartment, you have the copper ion and the nitrate ion present as well. Okay, so we are asked for the potential of the cell. Using the Nerst equation, assume that the condition is at room temperature. Since it's not stated here, we can assume it is at room temperature. So we can use the compressed equation for the Nerst at room temperature of 298 degrees Kelvin. Okay, we have here the factor 0.0591 volt over N, where N is the number of electrons transferred during the reaction for the cell. Okay, so the next step is we determine the E, standard potential value. Okay, at standard condition, we can determine that by using the technique that we have learned in the previous episode using the standard potential table reduction. And the KQ will be based on the overall cell reaction. Again, preparing for your anode which undergo oxidation reaction, we have the zinc will undergo oxidation and 2 electrons. For that, using your standard potential table, again, zinc is positive 0.76 because it is negative here. So we take the reverse of the sign since we are using it at the anode. Then for the cathode, you have copper ion plus 2 electrons will give you the copper metal. Okay. For the potential, reduction potential, that is positive 0.34 volt. And that will give you positive 1.10 volt. That is spontaneous. Okay, for the overall cell reaction, so we have now the standard electrode potential. We have solved it now. Then we have now, from the overall cell reaction, we can determine your N and your KQ. Okay, we have the zinc solid plus copper ion in the aqueous solution will give you the zinc ion plus the copper. Okay, the 2 electrons will cancel out. So from the overall cell reaction, your N value is 2. Okay, that is 2 electrons per mole of the reaction. Okay, we have the N value now. For your KEQ, from your knowledge on writing chemical equilibrium, product over the reactant raised to the respective stoichiometric coefficient. So the solid is not written in the KEQ expression. So only the ion zinc of zinc. And on the reactant, we have copper positive 2 Okay, they are raised to 1, which is their coefficient, and the sink here is not written in the denominator like copper in the numerator because it is in solid state. Remember our discussion in writing expression for chemical equilibrium. The solid and liquid are not included in the chemical ratio because of the, or reaction ratio rather, because of the activity of solid and liquid is 1, and 1 raised to any number is 1. Okay. So we substitute the given here, and this value is your 0.40 over 4.8 times 10 to the negative 3. And that gives you the KEQ value. $83.33. So we plug in that value to the equation. So the potential of the cell at this non-standard condition, you have positive 1.0 volt minus 0.0591 volt over 2, then the log of 83.33, and that gives you a value of positive 1.04 volts. Okay, there is a decrease in the potential at the non-standard when the concentration of the ions are not 1 molar. The 1.10 volt, the concentration of the ions is at 1 molar condition at room temperature. But the concentration of the zinc nitrate is 0.4 molar, and for the copper nitrate is 4.8 times 10 to the negative 3. Okay. Okay, for the next example, we are given here 1/2 cell in a voltaic cell is constructed from a silver wire dipped in a silver nitrate solution of a known concentration. The other half consists of a zinc electrode in a 1 molar solution of zinc nitrate. A potential of 1.48 volt is measured for this cell. Use this information to calculate the concentration of the silver ion. So you are given here a silver and a silver electrode and a zinc electrode. Okay, here. So we will decide which will be at the anode and which will be at the cathode. Okay, in our previous discussion, the more active metal should be the anode, and the less active metal should be at the cathode to make the cell spontaneous. So referring to your activity series, you have here the zinc and silver here. So zinc obviously would be your anode and silver would be your cathode. So we have here the zinc and this one would be the silver. Okay, here you have the zinc solid as your electrode. Okay, and the potential is given, that is the E is 1.48 volt. The temperature is not specified, so we can assume it is at room temperature to simplify the computation. Okay, this is given. Okay, not given. And you are, by the way, you are given the concentration of the zinc nitrate. This is 1 molar zinc nitrate. So that means that if the zinc nitrate is in an aqueous solution, it will be ionized to zinc ion and nitrate ion. On the other hand, you have an unknown concentration of the zinc nitrate here. Silver nitrate, by the way. So here you will have silver ion. Okay. And the nitrate ion as well, because nitrate are very soluble in water. Okay, so they would be highly ionized in water. Okay. So moving on, we can solve that standard potential of the cell, meaning at standard condition when the concentration are both 1 molar. But in this case, this is the unknown. Okay. And the potential is 1.48 volt. Okay. So since the zinc is your anode, so we can have the anode half cell reaction. You have the zinc losing 2 electrons to be oxidized to zinc ion. Again, previously we have determined the potential for zinc as negative. -0.76 undergoing reduction. And since this is oxidation, so it's positive 0.76 volt. For the cathode, we have here the silver ion undergoing reduction, accepting the electron. So silver ion plus 1 electron will be reduced to silver solid. Okay. Okay, you have here silver in the aqueous solution of unknown concentration plus 1 electron will be reduced to silver solid. So referring to the reduction potential of silver, that is positive 0.80 volt. Undergo reduction. It is below hydrogen in activity series, therefore it will be highly undergo reduction reaction. So taking the overall cell reaction and the potential as well, summing them up. Okay, first we have to cross multiply because the number of electron loss and gain are not equal. So we have to multiply this by 2 to make these 2 electron and take it as is. So the 2 electron will cancel out. So you have zinc metal plus 2 moles of silver ion in the aqueous solution in the cathode. Okay, would give you zinc ion, the aqueous solution at the anode, plus 2 moles of silver solid. Okay. The overall cell reaction is 1.56 volt and it is positive. So it is spontaneous because we place correctly the more active metal at the anode and the less active metal at the cathode. So there will be a potential. Okay, so we have now the potential at the standard condition. And we have determined your N2. So the unknown is the KEQ. And we can write the KEQ value based on the valence equation. From the valence equation, N is 2 electron per mole of reaction. Okay. And your KEQ expression based from the balance equation. Okay, this is solid, it will not be included. So we have only the zinc raised to 1. And again, this is solid, it will not be included in your KEQ value expression. Only this ion, the silver, positive 1 raised to 2, because the coefficient, the stoichiometric coefficient in the balance equation is 2. Okay, next we solve manipulating this equation, the condensed Nerst equation, to solve for your KEQ. We can plug it here because we don't have this one. We have this value and we don't have this value. We have two unknowns in one equation. We need one more independent equation, and that is the Nerst equation. Okay, so next step. Is we manipulate the Nerst equation. We have the potential at a non-standard, which is given. We have the E naught, or the electrode potential at standard condition, 0.0591 volt over N, the log of KEQ. So you can have 0.0591 volt over N, the log of KEQ, is equal to the potential at standard minus the non-standard potential. To solve for the log of KEQ, we have the N times the difference in the standard and the non-standard over the factor 0.0591 volt. So we have 2, and we have 1.56 volt minus the given, which is 1.48 here. It's given in the problem. Over 0.0591 volt. And that will give you 2.707. So if you take the antilog, you have 509.3. Okay. So next step, since the KEQ is the zinc ion based on the balance equation again, and the silver ion square, we can compute the square. Okay, the given for the concentration of the zinc nitrate here is 1. Because how do we determine the zinc ion? Because the zinc nitrate will decompose to zinc ion and the nitrate ion. So whatever the concentration of the zinc nitrate is the zinc ion concentration as well. Okay. So we have 1 molar. You don't have to write the unit because of the bracket. 1.0. Okay. And the KQ is 5.09.3. So we have the silver ion concentration. Zero 0.44 molar, or 4.4 times 10 to the negative 2 molar. Okay, move on to the next number. We're given here, in a galvanic cell at 36 degrees Celsius, one half cell contains 0.010 molar hydrochloric acid and a platinum electrode over which hydrogen is bubbled at a pressure of 0.5 atmosphere. The other half cell is composed of a zinc electrode in a 0.0125 molar solution of nickel nitrate. You were asked to calculate the cell potential. Okay, so you are given a platinum electrode here where hydrogen is bubbled. Of course, that is gas. And you have a zinc electrode. Again, referring to your activity series of your metal, which should be at the anode and which should be your cathode. Okay, hydrogen and nickel here. So nickel is above hydrogen. So your anode would be nickel and your cathode is the platinum. Okay, so you have here the nickel as your anode. And this one is your platinum, where hydrogen gas is bubbled. Okay, that is what you meant by that. Okay, so you have the nickel, 0.125 molar of the nickel nitrate. And here we have 0.010 molar hydrochloric acid. So since this is a strong acid, it will be highly ionized in water. So you have the hydrogen ion and the chloride ion here. Here you have the nickel ion. Again, nitrate is highly ionized. So the nickel nitrate will be ionized to the nickel ion and the nitrate ion. Here, the hydrochloric acid will be ionized to hydrogen ion and the chloride ion. So these are the ion concentration of both. Okay, this one for the nickel. So therefore, you are given there the nickel ion concentration is 0.125 molar and the hydrogen ion is 0.010 molar. Okay, and the hydrogen gas is contained at 0.5 atmosphere. That is the concentration of the gas. For gases, the concentration is in terms of atmospheric pressure. Okay, so you are required to compute for the potential. Obviously, this is a non-standard condition because the temperature is other than 25 and the concentration of the ion is not 1 molar. So you are given the temperature at 36 degrees Celsius. So for Kelvin, that is 36 plus 273. That gives you a temperature of 309 Kelvin. Okay. So we can choose the condensed equation for the Nerst because the condition is not at room temperature. It is 36 degrees Celsius. So we have this is a constant, the F is a constant. We can determine the N and the K based on the balance equation. And also this one, wala tayo pa nito. And this is being asked, but we can compute this one. Okay. So moving on, we have to determine the potential at the standard condition. Okay, given this value, after analyzing the problem, we arrive in these values. Okay, now since we identify the anode be the nickel being more active than the reference cell hydrogen, okay, it is above the reference cell hydrogen. Okay, so we have the nickel that will undergo oxidation, meaning it will lose electron and plus 2 electron. Okay, we get the 2 state from the crisscross method. Remember your lesson on redox or assigning oxidation number. Okay, so electron will be migrating here towards there, and it is the hydrogen ion that will accept the electron 1, but since that is diatomic, we have hydrogen gas here. Okay, we have 2 to balance, and the potential is 0. Definitely you don't need to repair, you know that is the reference, so 0. So all we have to take a look is the potential of nickel with respect to hydrogen. Okay, nickel is 0. That is redox, so we have the negative of negative 0.25 volt, and that will make it positive. Okay, so it is positive 0.25 volt. Now we have our E, so we have determined your N being 2 electron that is transferred. Okay, and you have write the KEQ based on the balance equation. Okay, so we have nickel plus 2 hydrogen ion, the aqueous will give you the nickel ion and the hydrogen gas. Okay, so your N is 2 electron per the mole of reaction. Okay, the next we can compute for your KEQ based from the balance equation. Okay, gases and ions or a case molecule are involved, product over reactant. So we have nickel multiplied by the hydrogen gas over hydrogen ion square here. The nickel solid is not included. Okay, so we substitute the values. For the nickel, here we have 0.125. We don't have to write the M because that is the bracket is the molar concentration. The unit is the molar concentration. And for the hydrogen gas, we have 0.5. And for the 0.01 square. So that will give you a value of, so we plug in the value. So the unknown is the potential that is non-standard. We have positive 0.25 volt minus 2.303. The R value is 8.314. Our unit is okay. The mole electron will cancel out. The joule will cancel out. Okay, this is mole per mole of reaction as well. The unit there, so the mole cancel out, Kelvin cancel out. Then we have the log of 625. So the potential is positive 0.25 volt minus this whole thing. This is 0.086 volt. So the potential is positive 0.64 volts. Okay. Okay, that's all for the non-standard condition using computing the potential of a cell which is at a non-standard condition. Okay, next time we will have the electrolysis topic on electrolysis and calculation involving electrolysis. Okay, well then, see you in the next episode.